Welcome to qnawire.
Okay, so we're doing chapter 29, problem 55 here. So we have this device drawn here, which is called a betatron, and it's used to accelerate electrons to high energy. So what it consists of is there's a circular vacuum tube that's placed in a magnetic field produced by this north and south pole magnets up close to it. And the electromagnet produces a field that both keeps the electron in their circular orbit inside the tube and increases the speed of the electrons when B changes. So this B is not necessarily constant. Okay. So part A says, explain how the electrons are accelerated. Okay. So when we see from the drawing here that the B fields are downward, right? And if this B field is downward and increasing, this induces a circular electric field along the path, right? Along the tube. And that field applies an electric force to the electron, causing it to accelerate. Causing electron to accelerate. Cool. Okay, so part B now says, in what direction are the electrons moving shown in this figure as if we're looking down above. Okay, so if we're looking above here, we see this is our tube, right? And our B fields, if we're looking above, is pointing down, so that's into the page. Is our B field. So for the electrons to move in a circle, the magnetic force must provide a centripetal acceleration, which needs to be pointing in. So that means this needs to be the FB at all points. And if this is one way it could be going, or this is the other way it could be going. So V cross into the page is which way? Well, actually, so V upwards crossed into the page would give a force inwards, but the equation for the magnetic force is QV cross B, and we're talking about an electron which has a negative charge, so that's going to flip it the other way. So actually this velocity is the correct one. So that means which way is that going along the circle? When we're looking down, that is clockwise. Okay, so that's the way they're moving. So part C now asks, should B increase or decrease to accelerate the electrons? Well, again, by Lenz's law, we know that the force from the electric field on the electrons is just Q times the electric field. So since we have an electron, Q is negative, so we need the electric field to be going in the opposite direction that they are, the force needs to be. So to accelerate them, it needs to be, E needs to be, or F needs to be clockwise along the direction of their motion, which we already said was clockwise. And if F needs to be clockwise, that means the E produced needs to be counterclockwise along the path. Okay? So by Lenz's law, a current in this field would create an upward magnetic flux, right? So that means when the B field is negative, it must be increasing by Lenz's law. So that means increasing B field is the correct one to accelerate. So let me go ahead and circle that. That's the answer. Okay, and lastly, part D says the magnetic field is actually 60 Hertz AC, and it says show the electrons can be accelerated only during a quarter of the cycle. Okay, so we just said that the electrons are accelerated for an increasing B that is downward, right? So if B needs to be increasing and downward for it to accelerate, what does that mean for us? Okay, so if it's 60 hertz AC, that means the B as a function plotted as a function of time is going to look like something like this. The sine wave across these, right? So is pointing, it would be pointing upward for all of that portion of the time. So this portion of the time is pointing upward. So that's already not very much, right? That cuts out half of a whole wavelength. And now, so the points when it's pointing downward, we need it to be increasing and downward. Well, that cuts out this half. So the only section where the electrons can accelerate is this section, where that is a quarter of the whole wavelength, which means it's a quarter of the time. So therefore, that's why the electrons can only be accelerated during a quarter of the cycle, as it said, because the magnetic field is only increasing and downward for a quarter of the cycle. Okay.